Welcome to HotChips 23. Keynote 1, ARM Processor Evolution.
Okay, so this is Simon Segars is going to give our keynote talk. He joined ARM way at the beginning as the company's 16th employee about 20 years ago. And that's when everybody fit into a restored 17th century barn outside of Cambridge. He started his career at ARM as a design engineer and worked up through lots of different technical positions and management positions to become Vice President of Engineering. And he led the design of the ARM7 and the ARM9 thumb families. And those are processors that have shipped billions of units. Since he's been at ARM, he's also led the worldwide sales team, run the corporate business development, and been on the board of directors since 2005. A few years ago, he relocated with his family to California, to Palo Alto actually, to head up ARM's physical IP division, a business that's focused on enabling optimized implementation IPs for ARM-based SoCs. He's also a member of the SOI Industry Consortium and of the EDA Consortium. So I'll let him take over.
Thanks, Alan, and good afternoon, everyone. It's good to be back here at HotChips. I presented here in 1999 on a processor family we launched at the time called the 9E processor family. This was a small synthesizable core and a bunch of cache processors that we built around that. And that seems like an eternity ago in terms of my lifetime, and also seems like an eternity in terms of the way technology has evolved. And that's kind of what I'm going to talk about today. I'm going to talk about how technology has advanced over the years and where we see this going for the future. Firstly, before I talk about what we think is going to go on from the ARM perspective, I'm going to take you back in time a bit and talk about 1980s mobile computing. Now, the 1980s were a great decade. Some of us remember it for bad choices in hairstyles, bad choices in men's fashions, but it was actually a very good time for technology and some key technologies that came along which have really set up mobile computing today. Now, just kind of looking out through the audience, it looks like there's many people on some pretty cool technology devices right now, surfing the web and checking your stock portfolio, although you probably don't want to do that right now. If you came to HotChips in 1991, even though the conference hadn't actually been started, the coolest guys in the room would have been sitting working on one of these. This is the Osborne 1, and I found this picture on the website. I unfortunately don't have one. But why this was a landmark design was that it really was the first portable computer. I want to say portable, of course. You could kind of lug it from one mains outlet to another. When you bought all 25 pounds of it, it didn't actually come with a battery. That was an optional extra. But it did come with a power cable, I guess a long one as well. I do actually remember seeing one. I would have been at school at the time. A friend of my father's had one, and it was, just enormous. And the prospect of carrying it around or sitting it on your lap while you did some work just seemed pretty alien. But it was a pretty cool device, and it really has set the scene for how mobile computing has advanced since. Had a pretty small processor, just a 4 meg Z80 processor, a small amount of memory, but you could do a lot with it. You could do word processing, various what we now know as productivity applications. It ran the CPM operating system, so there was lots of applications available for it, real forerunner of today. And it was a pretty successful product. They sold 11,000 of them. It would run you roughly $1,800, which is a lot of money then. If you kind of roll that forward in terms of today's money, that would be about $4,000, and that's quite a lot to pay for a laptop. I'm guessing nobody in the room would pay that right now. It was big, it was heavy. It's technically too big to count as carry-on luggage for American Airlines, I found out. So it's not that portable. Fortunately, things have got a lot better. But for me, that was a landmark design. Now, a couple of years later at HotChips, the coolest guys in the room would have been on another form of mobile device, and you probably would have heard for the first time, please silence your mobile phones. Because what you would have seen is this device. This was launched in '83. This was the first portable cellular phone. I've actually got one here. It doesn't work, although the guy I bought it off of eBay said it did work last time he used it, but that was 20 years ago. Also, the aerial's got a bit broken, so the reception's not too hot either. Again, landmark design, in today's terms, dreadful. Charge it up for 10 hours and you'll get 30 minutes of talk time. That will barely cover my commute to work in the morning. But you could use it. It's a very usable device. You couldn't do texting on it. You couldn't hook up your Bluetooth headset because these things hadn't been invented. But what's good about it compared to today's products, it's so big that they can print the instruction manual on the inside of it. You just have to slip the battery off. That would cost you $4,000. A friend of mine at work had one. He had the car kit that came with it. Cost him $8,000. And that's a lot for a mobile phone. Again, in today's terms, $4,000 is worth about $9,000, and I don't think even AT&T would try and charge you that for a cell phone. Fortunately, things have got better. Today, state-of-the-art laptop in the kind of clamshell form factor, just like the Osborne, is the MacBook Air here. A lot more powerful processor, a lot more memory, a lot more storage. The Osborne, actually, you could get a modem for it as an optional extra. Good for hooking up to the internet when it got invented 10 years later. This thing is, of course, full of connectivity and fortunately weighs about 1/10 the weight of the Osborne itself. Interestingly, in absolute terms, roughly the same price, although in real terms it's about 1/3 cheaper. Very good device. Your phone's got a lot more useful as well. This is the Samsung Galaxy S2. This has been launched in various countries, gets launched here in the United States in a couple of weeks' time, and is widely complimented as the kind of state-of-the-art Android phone right now. Interestingly, the screen on this is not much smaller than the screen on the Osborne, and of course much higher resolution, so you can do some pretty useful things on it. You can surf the web, as I'm guessing a lot of you are right now. Check out the weather forecast in London. That was kind of random coincidence. It's got the London weather on it. Play Angry Birds and do all that sort of stuff. And what's really impressive about this is, in real terms, this will cost you about 1/20th of what the Motorola, or perhaps I should say the Google Dynatac would cost you. So very, very impressive. Fortunately, the world has moved on and we're all benefiting from it. And I'm guessing lots of you in the room are kind of making a living from these kind of technology advances. So the industry has advanced a lot, and one of the things that has really driven that has been communication. As we've gone through these various eras of computing, people talk about now being in the third era of computing. We've gone from mainframes, which were enormous, through minis, where very few people ever used them. Mainframes sat in a room that was air-conditioned, and only if you had the right key you could go in and play with it. And then through the late 80s and 90s, computers became personal. As the internet came along, we were able to hook them up to the web and find out what the weather was in London. It's usually raining. And get access to all kinds of other services. And what's happening now, of course, is that the internet is moving on to mobile devices in a big way. Sales of PCs are going down, while sales of handheld portable devices are going up at quite a phenomenal rate. So lots of applications here, and as we go forwards, people are now talking about this Internet of Things, where everything is connected to everything else. You have sensors in everything, from your washing machine to your running shoes. I'm guessing for most people the left shoe knows roughly where the right shoe is, but sensors are going to help there to track how good you are at running, upload your data onto the web, compare with your friends, track where you are in the world. Sensors just going in absolutely every part of society. And that's kind of good, offers up a whole range of opportunities and new applications. Pretty worrying as well, though, because of the security applications. Probably most of us aren't that comfortable in somebody else knowing where we are absolutely every minute of the day. And I'll come back to that security theme later on. So in all of this, power is a big issue. The power consumption of the devices I showed there has come down enormously. And that's just as well because batteries aren't really helping us power handheld things or portable things. But power has become a big issue and a big driver of the technology behind the advances in computing. And at ARM, we take power very seriously. We design our processors to be as low power as we possibly can and design them ground up in that way, and in that way have helped provide the CPU performance required for lots and lots of these devices. Now, as well as connectivity, there are some other pressures which are driving forwards technology, other evolutionary pressures. Functionality is one. I mean, when I first saw the Osborne, it was, didn't take too much to think about what else could go in there. The screen needed to be bigger, it needed a faster processor. Color LCD was probably a bit of a stretch for my brain at the time. But the functionality needed to go up. Same with the phone. It has an address book in there. You can look up your home phone number and dial it, but it didn't do much else. So functionality, the desire for functionality has driven the technology that's gone into these devices. Cost, clearly you look at the price of the Osborne, you look at the price of the Dynatac, very expensive. The cost needed to come down for those devices to ever move away from being just business-focused toys for the very rich to something that everybody on the planet can have. And what's great about technology today is pretty much everybody on the planet can have it because we have driven the cost down to a point where it's become very, very affordable. Then you have form factor. I like this. Everybody who walks in my office and sees it instantly picks it up and starts playing with it, unlike my BlackBerry. But it is too small. It just about fits in my briefcase, but not in my pocket. It doubles as a very good defensive weapon if somebody meets me in a dark alley, but needs to get smaller, as did the Osborne. And clearly we've done that. And I think there's ways to go on that as well. And then, of course, competition. As these products come out, it's interesting looking at the Osborne, where pretty soon after they launched, they're an interesting business case study because they kind of almost killed themselves by overhyping their own products. But at the same time, the IBM PC came along, and everybody could see the future of this. Everybody started building them, and that drove a lot of innovation, and that innovation has been good for everyone who's ever used it since, so very good for consumers. So that's kind of what's been going on the last 30 years. I'm going to talk about the last 20 years before we start looking forwards again. I'm going to look at ARM's evolution, what we've done, and kind of the role we've played in some of this technology. So as Alan mentioned earlier, ARM was formed in a 17th century barn in the middle of the Cambridgeshire countryside. A picture of this shown here, and he was working at Apple at the time and came and worked with us for a couple of years. The garages in Cambridgeshire aren't that large, aren't kind of usefully large enough to form a company in, so we had to go with this barn. Fortunately, it had a bit of work done on it since the 17th century and was quite a nice place to go and work. There was a field full of sheep next door. There was a turkey farm, very, very loud in kind of November time, very quiet in January time. And the company got formed by a spin-out of some engineers with the technology from a British computer company called Acorn. It was a joint venture with Apple. And they took 13 engineers and a CEO and started this company. So that was in November 1990. The company's just coming up on having its 21st birthday. Pretty small at the time I joined. I was employee number 16. We have about 2,000 employees now in about 13 different countries around the world. And our goal was to design low-power embedded 32-bit processors. And that was a novel thing at the time. Most processors came in a chip package, you soldered it onto a PCB, and you hooked it up to everything else you wanted. We were looking at embedding processors into ASICs, into systems on chip, even though that term hadn't been coined at the time. And our goal was to go and license these to semiconductor companies, most of whom at the time had their own processor architectures, so it was a bit tricky at first. But the goal was to never to manufacture them. Our first CEO, a guy called Robin Saxby, great megalomaniac, brought a whole lot of energy to the company. He used to say we would build silicon over his dead body, and he is still alive, and so we don't do that. Now, when I joined, I thought, well, there's these kind of crazy guys that I'm going to go and work with. I was pretty fresh out of university at the time, and after I joined, they let me into the secret that the reason the company had been formed was to actually build a processor for this thing, of course, the Apple Newton. And this really was a great attempt to build a very, very portable handheld computer. They obviously succeeded in that. It launched, wasn't the world's most successful consumer product, but the weight was very, very low, just under 1.5 pounds. The battery life was really good, ran off AA batteries for a long time, and gave you a lot of applications in your hand. Now, one of the problems with it was there was very little connectivity. There was a Apple, I can't remember the name of the Apple Talk connector on the side of it. There was no Wi-Fi because, again, it hadn't been invented at the time. So it really was captive to you. You couldn't connect it to anything. Now, we were always looking for good ways for our technology to be used, and whilst the Newton wasn't quite the success we hoped it would be, we got talking to people who were building cell phones. And at the time, most cell phones were analog. Digital was just coming about. GSM was just starting to be established as a technology. And the people making the early phones wanted to have a more powerful processor. They wanted a 32-bit processor because they wanted all the benefits that was going to bring. But the problem was that the code size that a RISC processor could give you was too big. So it was going to make the cost of the end unit too much. So we went away and thought about this and came up with a way of encoding our 32-bit instructions into a 16-bit instruction set. We called that Thumb, and we built this chip called the ARM7 TDMI. I won't go into all the letters stand for, but it was commonly known as Thumb. This was small, only 74,000 transistors, which is tiny by today's standards. I'm sure most of the chips you've seen this morning, this would be a speck of dust in the corner. But we had to work really hard at the time to get the area down. It's only built with 2 layers of metal. We had a massively manual design process, and we had some very demanding customers trying to get us to make it as small as possible, because what they wanted to do was integrate it into a chip with a DSP, with some control logic, and put that into a cell phone. And that they did. Our early customers did that. And GSM phones turned out to be pretty popular. And the ARM7 really became the de facto standard for 2G cellular. I think you'd find it very hard to buy a 2G phone that did not have that processor in. It's also been used in lots and lots of other things. It's been massively successful. And in combination, our licensees have shipped close on 15 billion chips containing that ARM7. It's been ported to lots of different technologies. We started off on 0.5 micron. We ported it recently to 28 nanometers, and it's still getting designed into things. So it's been a very useful design. This is the Nokia 6110. Again, for me, another landmark device because it brought together a lot of good technology into an incredibly useful cell phone. The battery would last for a week, and that was pretty good. Very basic user interface, though. The processor was being used to run the protocol stack in the baseband, and the spare performance that was left over ran the UI, and it ran the applications such that they were the contact list, the calendar, Snake, great game. And of course, you could send lots of SMS messages. Nobody knew quite how successful that would be or how popular, but clearly it was. So great device. These were robust. You could throw them down a flight of stairs and they would still work, lasted forever. But not exactly what you'd call a mobile computer, despite for me it being a real landmark device. Now, we're talking about evolution, and evolution in species happen when genetically successful parents combine to produce a new offspring. We've been working on these kind of devices, and when you think about it, that really was the evolutionary combination of those two things form smartphones that we all know today, and I bet most of you in the room have got something like this. So the technologies all came together. 15 years of technology evolution in the meantime helped a lot, and we now have a whole bunch of very useful products. In that time, Moore's law has helped us. Continual transistor scaling has helped turn those very basic devices into something very, very useful. The plot here is the ARM1. This was built by the team in Acorn before ARM was formed in 1985 on 3-micron technology, about 6,000 gates, in a chip that was 7x7. And all we could put in the 7x7, or they could put in the 7x7 chip at the time, was this processor. It was a standalone chip. Now, it turns out 7x7 is a very economical sweet spot to go and build chips with. In today's technology, you can fit about 1,400 die on a 300 mil wafer in 7x7, and it turns out to be a fairly constant die size that people want to look for when producing low-cost consumer devices. So that was ARM1 in 1985. This is the plot of a 20 nanometer test chip that we taped out in December. And inside that is a processor we call Cortex M0. This is the smallest processor that we sell right now. And that's kind of in the middle there. Very small, about 8K gates, so roughly the same size, runs a little bit faster, but not that much, which doesn't sound like much progress. But it's a 10,000th of the size. And so when we put that in that 7x7 die, we've got a lot of room left over. And that room gets used by anyone and everyone to fill it up with useful things to make much more useful devices than just standalone CPUs that you have to solder onto a board. Now, we use that. We build much more sophisticated microprocessors these days. This is a plot of one of our customers' chips containing a dual-core Cortex A9. This is one of our flagship products right now. A graphics core, the Mali 400, with room left over for all the rest of the system, all the I/O, high-speed DDR. But again, it's roughly 50 square millimeters. So that die size has kind of remained constant. What we can do with it, much more useful because of the design advances we've made over the years, backed up by consistent transistor scaling produced by the guys who build foundries. So that's what's been going on. And you may think, well, great, let's just do this again for the next 30 years, and we will be saying, beam me up, Scotty, and everything will be good. But I think that although we've made fantastic progress, and you all in the room have contributed to that, I think there are a few issues ahead. I'm going to touch on some of those because I don't think the future is going to be quite like the past. So first, the good news. Cell phones clearly taken off in a big way. Smartphones taking off in a big way. Tablets starting off big way. Everything around this technology is big. All the numbers are big. Last year, 280 million smartphones were shipped. There are billions of people or billions of cellular connections on the planet. These devices are getting used for e-commerce now. Smartphone applications just gone through the roof. A few years ago, nobody really would have thought that. It's happening in a big way, and it's happening very quickly. Cellular networks are getting higher bandwidth. And I think that's going to trigger a new phase of things we will do with these devices. And in the developing world, smartphones are starting to take off as well and replace PCs or in fact, leapfrog over PCs in the evolution of technology in those places. So everything about this is big. It's a huge opportunity. Now we've just got to deliver on it. One of our marketing guys gave me this slide, which I think is slightly overcomplicated. So just to explain this, on the right-hand axis there, you have smartphone volume as it's grown and how it's projected to grow. And then the blue blobs are the ARM processors, and on the left-hand axis, you've got the relative performance of those ARM processors. And I was looking at this, and you can see clearly there's a couple of inflection points here, and I was thinking about this, what those inflection points were. Because it kind of divides this space into three phases. Phase one, very early smartphones. These were the communicator-style devices where there was a couple of issues. There was extreme power constraint on the processor, which means we could only put a couple of 100 megahertz processor in it. And at the same time, people designing these were really thinking of the PC or the laptop usage paradigm. So really, that was a small laptop. Small keyboard, small screen. You had to be a pretty brave man to try and do some real work on that, but you could. So what happened in phase two? Well, I think a couple of things happened. We created this product called ARM11, which gave much more performance. And that combined with advances in process technology meant we could run it at lower voltages. Meant you could get more life out of the battery, and you could do more with the device. In parallel with that, the touch screen came along, and the first touch devices were launched. And that really determined a different usage paradigm for the smartphone. And it kicked off the whole application world and just meant that people were able to use these devices to do things differently. That turned out people weren't looking for small PCs that were cheap and they could put in their pocket. They were looking to do something different. And this has enabled a whole new way of communicating between different humans on the planet. So that spurred a big growth, I think, touch screen and the performance that we could enable. But at that time, 3G hadn't really come along. 3G came along during that period, and then suddenly we could get some useful data into it as well. And that's enabled us to enter phase three. Again, we're producing higher performance processors. The transistor scaling has helped us delivering those, get more transistors on the chip for the same cost, get more power out, deliver higher performance. And that, combined with the higher data networks, is enabling more and more things to be done with these devices. So yeah, personally, I was quite interested in drawing those conclusions about this three-phase and what's changing that. And as we go forwards, of course, smartphones and tablets are an extension of this kind of device. And I think with LTE coming along, as it now is, we'll see even higher data going in, and we'll see new usage models appearing for both the smartphone and the tablet. So as we look forward to smartphones, of course, again, marketing guys going to town, you've now got the Superphone. You had the smartphone, now you've got the Superphone. I'm not quite sure what's going to come next, but some other superlative phone will be out in the future. And this is the kind of device that people are looking at designing now for delivery in a couple of years' time. The goal being, this is the thing you use to surf the web, stay connected with your friends on other continents that you knew 30 years ago, with enough compute power to replace your laptop. Now, obviously, you're going to need some probably Bluetooth-enabled docking station to hook you up to a keyboard and a screen to really do that. But all those technologies exist. That can be done. Very visual experience is going to give you lots of video, high-definition video, cameras all over it, and the ability to hook it up to your big screen TV at home. So again, it is just the thing that contains your life. That's going to need a whole load of software. I'll come on to that. And it's going to be enabled by lots of processing inside it. And a key thing that we're looking at, and a key thing I think as an industry we need to think about, is heterogeneous multi-processing enabling a device like this. And the reason we're going to need to do that is to contain power. And I'll come back to that. As we look out at smartphone growth, mobile phones in general have been kind of split into three categories. Basic voice phone, what they call feature phone, and then smartphone. Smartphone growing big time. That itself is now being categorized into three different areas. At the top, you have this Superphone. Down the bottom, you have this entry-level phone. And in the middle is something that's in the middle that will probably get squeezed out over time, just like feature phone did. Now, the bottom, big opportunity there. People are talking about potentially billions of units of this over time to enable new markets. So you'll probably, given we're in the home of the early adopter, have got the kind of superphone end of things right now. There's whole continents of people who are starting to use phones for e-commerce who aren't going to be able to afford that $500 device and want something much less. This $100 to $200 price bracket is an important thing to hit to enable very high volumes in markets that are not characterized by the kind of people who live in Palo Alto. Now, everybody wants this. Consumers want it, clearly. OEMs want to deliver them. Mobile operators want this to drive data across their networks and drive their revenues up. So there's a lot of demand for this kind of device. Running Android, because of the open model and the free access to the operating system, helps keep the cost low. But with all the benefits of a full browser, all the web standards to enable video, Flash and HTML5, and access to the Android marketplace. So this is a phone that a lot of people are working on because the market is big, and you're likely to see this start to emerge over the next couple of years. Now, all of that needs a whole load of software. As we've delivered more and more compute power, and we've seen this in the PC space, and we're seeing it in the mobile space, software engineers love, just soaking that all up and using it to deliver, cool functionality, most of which is useful, and some of it's maybe not so useful. But clearly, there's going to be a whole load of software written for and run on these devices. And as the operating systems are very open, and as we want to encourage as many people to write applications and do things with phones that the guys who designed them in the first place didn't really contemplate at the time, you need standards, you need openness. And the downside of that is that supporting standards, supporting these interfaces requires more and more compute power. So it's really important that we deliver this software in a very efficient way, and that there's a lot of collaboration across this whole space to make sure that the code is written efficiently, recognizing the fact that you haven't just got one big hunking processor with a whole load of memory sat next to it and a hard drive. You've got a very different set of hardware resources to utilize, and you need to do that in an efficient way if you want to get any form of battery life out of this device. So lots of software, lots of pieces of technology, and it requires that collaboration to do it in an efficient way. And that's a key tenet of what ARM does. So this device is probably at the center of most of your worlds right now. and and it's just going to become more so as we go forwards. And we've got here some examples of things people do with their phones right now. These are all things you can do today. So you can get an application for your phone that will let you start your car. You can swing by Starbucks and buy yourself a coffee on it. You can monitor your house security. Set the alarm, unset the alarm, see what's happening, see what your kids are up to. Your video services can be managed through this, and communication with your family and your friends overseas can all move from the desktop via maybe your lounge room and onto your mobile phone. So lots of things you're going to want to do with your phone, you're starting to be able to do today. And one of the concerns about that, whilst that's great, is it does raise the risk of security issues. And we see security as a big thing. Now, this phone, the Dynasag, as I said, it kind of serves as a bit of a deterrent, but your average smartphone today, being very small, is not indeed the case. So I thought I'd go for a bit of audience participation here. When it comes to security, something we often talk about at work is a man walks up to you on a dark night, dark rainy night with a gun, and he says, "I'm going to shoot you unless you give me either your wallet or your phone." So show of hands, who gives the wallet? And who gives the phone? Okay, so today most people get going with the phone. I reckon in the future, when there's a lot of your life on there, information about your medical records, all sorts of information about you might actually change your mind on that. What's going to be required is a good security solution. And this is something that we have been worrying about for quite a long time. Back in about 2002, we launched a technology called TrustZone in one of our ARM11 processors. And we thought this was going to be a big deal, but it turned out at the time nobody really cared about it because we were thinking about DRM, and frankly, who cares about DRM? Most people are trying to avoid it. But as more of your life migrates to this phone, security is becoming a bigger deal. So we have this technology called TrustZone, recognizing that security is much more than just some software. We've actually put hooks deep into the architecture, deep in the registers, and in the way that the hardware deals with memory to allow you to create a secure environment for software to run in your system. We create these domains, a regular normal domain and a secure domain, and that can get then implemented across the entire SoC. So information can get put out on the pins of the chip or between the processor and the memory system to denote what mode it's in, and make sure that only trusted applications can get access to areas of memory where security keys are kept and where your medical records are, for example. So that enables us to build a complete SoC with a secure operating system on top. Your operating system can have a secure kernel. It can move between the regular mode, which is less secure, and the secure mode in a controlled way, and creates this trusted environment on top of which you can build applications for dealing with e-commerce in a secure way. And we have some partnerships going which are utilizing this technology. TrustZone has been put out in some of the chips that our partners have built, and we're starting to see secure applications built on top of it. So security, big step, big issue. We have some solutions, hopefully. So big markets, lots of potential, lots of opportunities, but there are a few areas that I think are challenging, and I'm going to talk briefly about 4 here. First is modems, then actually implementing a chip, then battery scaling, which is a bit of a problem, and finally transistor scaling. So first about modems. Now, mobile devices rely on being able to get data in and out of them, and that is a computationally expensive thing to do. This graph shows the relative performance required, relative compute performance required to implement different classes of modem. Now, 2G back in the early 90s was a hard problem, and it was solved with a general purpose processor, a DSP, bit of control logic, but essentially it was a programmable thing. Now, it was hard then. By today's standards, that was a complete walk in the park. A 4G modem, which is going to deliver about 100x the bandwidth of a 3.9G modem, is going to be about 500 times more complex than a 2G solution. And increasingly, it's moved away from some programmable processors, DSP and a CPU that you code up, towards more dedicated hardware engines, which are going to perform the DSP functions, which are extreme, We're kind of at the limit of how much data you can put across the available spectrum. So you need a ton of DSP to actually do that. Still need a control processor, but you need these dedicated processing engines. Now, we kind of have to go that way anyway because of the power, but we have to go there too because of the performance required. So this is a problem. Hard DSP task, going to take up more silicon area. That's not so bad because silicon's being scaled the whole time, but it's going to eat a lot of power, and the power is the real problem. And the reason for that is because batteries are pretty rubbish, really. Historically, battery capacity has grown by about 10 or 11% per year, which unfortunately is not very well matched with Moore's law. Transistors have got a lot more faster, leakage has started to become an issue, so new sources of power consumption have come along. And even just to maintain that 11% as we go forwards requires some pretty exotic materials, which I do not claim to be an expert on in the slightest way, but I do know that it's a big problem. Batteries have got a bit smaller in the devices. As I said, they've grown about 11%, but that isn't very good when we look at the problems that we're trying to solve. What you really need is a new battery. If somebody can work out how to hook up a chocolate bar into their cell phone, that would be pretty good because there's about 35 times the energy density out of a bar of Cadbury's Dairy Milk here. And that might help us solve our power problem. When you look at the capacity of a battery today, you get about 5,700 milliwatt hours out of a battery that you could take out of your cell phone right now. And to run your device, what we say, all day, so if you run it flat out for 12 hours, you need all your electronics to dissipate less than half a watt of power. Now, this is why you have to charge your phone up every day, because there's a lot of electronics in it, and half a watt is a bit difficult. And to get that down to a 3-day life, and remember that's still less than half we had with the Nokia 6110, you'd need to reduce that to 159 milliwatts. Pretty difficult. With 10 years of evolution at 11%, we get up to 13,000 milliwatt hours, and that gives us a watt to play with if we want to run a 1 day. And that's starting to get useful, but it's still not that useful given all the computing constraints of 4G modems and the CPUs and the video and the graphics that people want to do with them. So batteries not helping us at the moment. And then there's implementation, going back to my favorite 32-bit processor. This was small and simple, very manual flow. We didn't even have a timing tool that could absorb the whole design and tell us whether it was timing clean. We had to do this piecemeal and very manually. Very simple to sign off, though. We only had 3 corners and 1 voltage domain to worry about. This is Cortex-A9. This is a dual-core implementation of it. Transistor count's gone up enormously. Die size actually smaller, but of course we've got 28 nanometer technology to play with these days. Much more complex timing sign-off. Over 12 corners. Many of our customers tape out sign-off with more corners than that. Multiple voltage domains, and new physics issues you have to worry about as you finish this chip and get it taped out. And you really, really need to worry about that because the cost of your tape out is going to be astronomical. When you've written that check for $1 million or $2 million for your masks, you want to hope that chip works. So the effort going into validating and verifying your design has gone up by orders of magnitude as well in this period. Now, ARM7, pretty small compared with the Cortex-A9, and hence that kind of represents the scale of the problem that we have now. Now, one other thing that's happened over the last, I guess 40 years, is the way that the industry itself has changed. When people first started building semiconductor devices, they did everything themselves in fully vertically integrated companies. People had fabs, product design, manufacturing, case design, did the whole thing themselves. Fortunately, over the years, this has disaggregated. We've gone through ASIC models. Now pretty much everyone's a fabless semiconductor company. And people have started adopting more and more IP to put their designs together. Now that's been good because it's helped lower cost across the industry. The fabs came up kind of recognizing that there was an economy of scale that could be had if you could build a fab and manufacture pretty much anyone's silicon to make some choices about the process you were going to run, but there was a big cost saving to be had, and that has enabled over this time period more and more people to do semiconductor design, and I think that's really helped with the innovation that we've seen in all of these products that I've been talking about. So that's been great, it's helped lower cost, But unfortunately, as more and more people have migrated to just worrying about design, then those skills you need to close out the timing at the transistor level are kind of becoming a dying art. And as we go forwards and start worrying about very exotic processes that we're going to have to deal with in the future, those transistor skills are going to need to become very, very important once again. And as a designer, you're going to have to worry about everything from architecture down to transistors if you're to deliver more and more performance each year whilst keeping the cost down and the power down. So disaggregation has had its pros and cons. Now, fabs themselves, somebody once said that real men own fabs, although they're not as popular as they used to be. In parallel with the disaggregation of the industry and the foundries, the pure play foundries that sprung up, being able to amortize cost and get the cost down, we've seen the cost of developing processes go up and up and up. It now costs you billions of dollars, as I'm sure everybody knows, to develop a new process. It costs you billions of dollars to buy all the equipment for it. So fewer people are doing it. And as the foundries are producing leading edge processes now, everyone can go to this fabless model. Now, that sounds great. But the downside is the physics problems that you have to solve as you go to smaller and smaller geometries are getting harder and harder to solve. And so the cost of the equipment that you need for the next generation process goes up and up. Now, again, what's the problem here? Well, the problem is that the supply chain that builds that equipment for the foundries has a bit of trouble dealing with its return on investment. Now, when the world moved from 200 mil wafers to 300 mil wafers, if you were ASML or something like that, you had a whole lot of customers you could go and sell that equipment to. Right now, people are talking about how quickly can we move to 450, because again, it should bring an economy of scale there. But there's only going to be about 4 guys who are going to build those size wafers. So if you're doing all the R&D and your customer size is 4, that is a bit of a problem. So although the industry has delivered successive reductions in size, reductions in power, and increases in performance, I think there are some challenges ahead as we scale devices. It's been great. I've got to say, if you've been involved in the technology to shrink from 65 or 3 microns down to 20 nanometers that we have customers looking at today, then frankly, you should give yourself a huge pat on the back, because the science involved in doing that has been astronomical. And to do that, we've had to see some fairly significant technologies come along. As we went to 40 nanometer, strain got involved, and the strain on those transistors is quite astronomical. We've seen high K materials come along to get us into 32 and 28, and these have enabled us to kind of step up, but they're kind of one-trick ponies. Every generation, you've got to think of something new. Now, we're doing a lot of experimentation around 20 nanometer right now, and the problem here is that you need to introduce double patterning. So, as I'm sure you all know, we've used 193 nanometer wavelength light to draw all these features, which are getting smaller and smaller, and that gets harder and harder each time round. And so people are now using 2 sets of masks to draw what they could do in 1. That's a problem because of cost. With twice the processing, the throughput of your fab goes down. You have to spend more on equipment to keep the throughput up, and so on. So the cost issues of going to these next generation technologies are getting really, really hard. And that's not going to help us deliver against all that opportunity. At 14 and below, what you really want is EUV. EUV will give you 13.5 nanometer wavelength light. That would be really useful for drawing these. Problem is, it's really, really hard to make. You've got to make this plasma out of tin atoms and then shoot it with a laser, and then some light comes out. But the light's really weak, and it gets absorbed by everything. And so generating enough of it to economically build chips, very, very hard. To have a fab running economically, you need to build about 200 to 300 wafers an hour. EUV machines today can do about 5. So a long way to go before that is a mainstream technology. And some people I've spoken to question whether it in fact ever will. So if that's the case, then frankly, I'm not quite sure what we're going to do to get the scaling up. Big problem, lots of R&D needs to go in that. For the future, people are looking at alternate materials. You can only scale silicon so far. A silicon atom has a diameter of 0.27, I think it is, nanometers. So you haven't got very many of them in a 20 nanometer length transistor. You can only scale that so far. and so we need to look at other materials. And again, lots of R&D going into 3.5 semiconductors. They have their issues as well, but offer potentially much higher mobilities to allow us to deliver more performance. So this is a challenge as I see it. So I think solving all of these is going to require us to think differently. The future is going to be about multiprocessing, heterogeneous multiprocessing, picking a processor that's most suited for the task that you have to run. That means lots of hardware. That means lots of focus on power control, implementing multiple power domains, and lots of focus on the software that's then going to run on those devices. There's a standard called OpenCL coming out of the Kronos group right now that is about how you map applications across a sea of heterogeneous processors and pick the most appropriate one for the task. That's very encouraging, and I think we're going to need to do that so we can deliver the kind of performance that we want. That heterogeneous multiprocessing array is probably going to be built on a heterogeneous stack of different die, hopefully slightly more elegantly than the stack shown here. But I think this is a really interesting development. You could have a high-performance logic die, your DRAM, your flash, maybe an analog die built in, say, 65 nanometer, all in the same stack, all hooked up through TSV or some other exotic interconnect technology. Again, lots of science required on that. But it's going to enable us to think differently about design, think differently about how we manufacture these chips and take them to market. Now, for us, advanced processing right now is about delivering on a lot of this, delivering on homogeneous multiprocessing as well as heterogeneous. Our flagship product right now is the Cortex-A15. This is a high-end, power-efficient processor. This has a pipeline which is 5 times deeper than that of the ARM7, a 15-stage pipeline, and that's if you're just running regular instructions. A lot of functionality in there. Again, we've designed it ground up for low power, but also thinking about the system that it's going to be designed into. And one of the features that we've really focused on is enabling coherent interconnect between different processors and different clusters of processor in a system. The A15 can be implemented in a completely fully coherent quad-core cluster, and then through our coherent bus interconnect, it can talk to another cluster of Cortex-A15s in a fully coherent way, and then talk to any other bus master that's in the system and export information about its coherency to try and keep the whole system coherent. So we put a lot of effort into that. We think this is important. We think it's an important way to simplify software, because without the coherency features, your software's got to deal with it. That's going to make software more complex. It's going to make software more power consuming. And so it's going to help with that, and it's going to help keep power down as well. So as we step up to the SoC level, we see different levels of coherency coming along. Right now, people are building Cortex-A9s with full coherency. I think you're going to see a demo of one of them a bit later on, actually. But coherent within the CPU cluster. To be coherent with the rest of the system, as I said, you have to either not do it or let software do it, and that takes power. Coming soon, we have Cortex-A15 devices. As I said, they can be coherent within themselves and export coherency to a graphics or a video system. In our case here, our graphics core can actually watch what's going on inside the A15, detect when there's a coherency issue, and then force data to be flushed out of the A15's cache. But again, that's kind of coherency happening at the I/O level. As we go forwards, we see the implementation of full coherency, where the different bus masters can share information, clean each other's caches, and save data being transported around the chip and through memory, and that saves power. So as a wrap up here, I think key message, we've come a long way, but to enable these devices of the future requires a holistic approach to SoC design. It's not good enough to worry about bits and bytes. You've got to worry about software, architecture, the algorithms you're going to run, the networks you're going to connect to, all the way down to the transistors. And so that's a key thing that we think is really important, and a key thing that we're trying to drive from within ARM. So in conclusion, I think the last 30 years have delivered some incredible gains in technology. We've gone from Dynatacs and Osborne computers to things which can now fit in your pocket and not burn a hole in them either because of the power they consume or the cost of them. That has been great. We're seeing that's going to continue. The demand for that is going to continue into the future. And our challenge then is actually producing the technology to deliver on that opportunity. The silicon scaling has been great. We've got huge gains in power, performance, and area, but it's going to end somewhere, and that's going to affect how we do design, how we run our businesses. So, my advice to you is get ready for that because it's coming sooner than a lot of people want to recognize. And I think the future of processing is heterogeneous multiprocessing. Multi-core CPUs, multi-CPUs, dedicated engines, arranged in various clusters with a software layer that can understand the underlying hardware and make sure that if it's not needed, it's shut off, it's not leaking, to preserve that battery. Because batteries really aren't helping you very much. What we really need is a new one. So if anyone's got an idea about the chocolate bar, then I'd be really glad to hear it. And with that, thank you very much.
Hi, Al Wegener, Samplify Systems. I observed that both Intel x86 multi-cores as well as GPUs from NVIDIA, especially the Fermi with 512 cores, they seem to have more of an I/O problem than a compute problem. Is ARM doing anything special to address the getting bits to all those cores problem?
Well, we worry a lot about that interconnect. So we have a whole team of people who are worrying about how we get data transported around the chip in an efficient way, how we get it off out into external memory and brought back in. If you take the NVIDIA example that you just gave, I mean, I think that's at a level of performance that is probably not supported by a small battery. So the scale of the problem is a bit different. But certainly moving data around the chip, trying to minimize it, is absolutely something that we're looking at. And these features we're adding for coherency are certainly in that direction.
Todd Besnick, Quantum, the follow-on, perfect for this. Can you explain how adding coherency, that means more dynamic power used, actually saves power? It seems like it's cheaper just to use messages and send data where it needs to be instead of use expensive hardware coherency.
Well, I guess the goal is to try and message what needs to change through the hardware, as opposed to have to run software to try and work that out. So we're trying to reduce the amount of instructions that get fetched out of memory, cycled through the processor, to then work out that there's a problem that you've then got to solve. So by having a direct link in the hardware, you can message that quickly without needing the CPU to do some work. So it's like having a dedicated engine to do something. If you know what you're doing, it's the cheapest way to do it in terms of power.
Other questions? All right.
Okay. Well, again, thank you.